Hi class, welcome to exercise 1K, simultaneous equations using elimination. So obviously we're continuing with our simultaneous equation journey, but we're learning a new method called elimination. And in this exercise we'll have example 29 using the elimination method with matching pairs of terms. And your pre-learning in the new book will be questions 1 and 2, and in the old book it'll be question 4. Then we'll do example 30 using the elimination method to solve simultaneous equations, where the pre-learning in the new book is questions 3 and 4, and for the old book is questions 5 and 6. In this lesson we'll carefully cover the algebra concepts behind simultaneous equations, particularly relating to the elimination method, but we'll also look at how they relate to the graphs, and there'll be some parts of the lessons where I swap over to GeoGebra. Please pay attention all the way through, and I suggest you might want to take your notes at the end because the algebra rules that I give you will make more sense after you've seen some numbers. Alright, let's get on with the introduction. In the last class we introduced the concept of simultaneous equations. This meant we found a solution for two different linear relations that are describing interactions between the same two variables. Throughout this unit we've learnt how to graph linear relations, and in the previous lesson we saw how the solution to a pair of simultaneous equations can be represented as the intersection of the lines we draw when we graph these relations. We then use a substitution method to solve them. This relied upon finding a relation of the form y equals mx plus c. However, sometimes it's not convenient to find a relation of that form, especially when the description of the two variables we're interested in, which I'll call x and y, may have the form ax plus by equals c and dx plus ey equals f, which I'll number 1 and 2 like I did in the previous lesson. So in this lesson we'll learn the elimination method, which allows us to leave our relations in this form. Okay, so here are some fun facts that will both show us why we can use this method and spell out some rules that we have to stick to while using this method. So imagine we have a relation 2x plus 3y equals 6 and graphed it on these roughly drawn axes. Using the intercept method, when x is 0, y has to be equal to 2, and when y is 0, x has to be equal to 3. So we'd end up with this line here. So now imagine if I multiplied both sides of this equation by 2, we'd end up with 4x plus 6y equals 12. And then to graph this one on the same axes, using the intercept method, when x is 0, y would have to equal 2. And of course the x-intercept is where y equals 0, which is x equals to 3. And then drawing the straight line between those 2 points, wow, surprise, surprise, we have the same relation, despite my bad drawing. So you can come back later and write this down as a rule. Fact 1. If we have a linear relation, ax plus by is equal to c, if I multiply both sides of the equation by the same number, then I essentially still have the same relation. If you're the sort of person that needs more than a teacher saying, trust me, why don't you write out both of these equations above, then convert both into a relation of the form y equals mx plus c, and see if you can now trust this fact. Okay, let's move on to the next key idea. Now if I told you I had a variable x and it was equal to 3, and I had another variable y that was equal to 5, then I'm guessing you'd have no problem saying x plus y equals 5, or x minus y equals minus 2. So we can extend this idea to fact 2, which is saying if I have an equation ax plus by equal to c, which I'll name equation 1, and another equation dx plus ey equals f, which we'll name equation 2, then adding equation 1 and 2 together would give us ax plus by plus dx plus ey is equal to c plus f, which when I collect like terms becomes a plus d times x and b plus e times y equal to c plus f. And therefore our new coefficient of x is a plus d and our coefficient of y is b plus e. But just please note that we'll skip this step in the examples. And from this point, if a plus d is equal to 0, we've eliminated x and can solve for y. Similarly, if b plus e is equal to 0, we've eliminated the y variable and can solve for x. Alternatively, we might want to subtract equation 2 from equation 1, and then we'd end up with a minus d times x plus b minus e times y equal to c minus f. And of course, if a minus d is 0, then we've eliminated x and can solve for y, and if b minus e is 0, we've eliminated y and can solve for x. Okay, it's really important to note that these relations must remain linear, so that means you can't multiply them together. So if we go back and say x is equal to 3 and y is equal to 5, you'll be happy to say that x times y is equal to 15. But we can't say that ax plus by times dx plus ey is equal to c times d, because we're going to end up with an x or y squared or an x times y, and that is no longer a linear relation. Also note that fact 1 and fact 2 means that the concept of visualizing the solution of simultaneous equations as the intersection of two lines is still valid, which also means that if the relations are parallel lines, there's no solution. The elimination method is simply just using fact 1 and 2 together to eliminate one of the variables of the linear relations so that we can solve the other one. Typically by variables I mean x and y. As I said earlier, using all this algebra to explain the rules of the elimination method could be confusing for you. If that's true, wait until you see me use actual numbers in the examples, then it should be much clearer for you. After you see the examples work with the numbers, then I recommend that you take notes with the algebra, because you can then use the algebra-based notes to remember this method for any question. At the completion of each example in OneNote, I'm going to show you the solutions all over again in GeoGebra. This is to make sure that you see that the solutions are still just the intersection between lines. At the very end, I'm also going to use GeoGebra to demonstrate why fact 1 is true. Okay, I'll see you in the next section. Okay, in this section we're going to actually apply the elimination method. And as I stated in the introduction, we just use fact 1 and fact 2 as needed. Okay, so let me explain exactly how we use them now. So first off, we number our equations 1 and 2. Then if we were to use fact 1, we would write 2 times equation 1 if we wanted to multiply the first equation by 2. Then we give our new relation a new number. In other words, if I let our first equation be 3x plus y equals 3, then 2 times 1 would be 6x plus 2y equals 6, which we then might name 3, assuming we've already got an equation named 2. Sometimes we don't need fact 1, but if we do need fact 1, we apply it to either one or both of the equations until there's a matching coefficient for one of the variables. When we do have a matching pair of coefficients for either x or y, we then use fact 2, and don't forget we only need to focus on adding and subtracting like terms. Alright, let's try this in example 29, where we won't need to use fact 1, because in this example we're given simultaneous equations with a matching pair of terms. And the equations we need to solve simultaneously are x plus y equals 6, which we'll name equation 1, and 3x minus y equals 10, which I'll name equation 2. So by matching pair, or same coefficient, we mean that in this case, y is multiplied by 1 in both equations. But because it's plus y in the first one and minus y in the second one, if we added them together, the y's would disappear. So this is why we don't need fact 1. So equation 1 plus equation 2 is x plus 3x is 4x, 0y, we can ignore that, equals 6 plus 10 is 16. So in other words, x is equal to 4. So now that we've already solved for x, we just need to sub this value of x into either of the equations, and clearly the first one is easiest. So subbing in that 4 for x gives us 4 plus y equals 6. So in other words, y is equal to 2. So I probably should have written subbing x equals 4 into equation 1. So clearly it works in equation 1. Let's try it out for equation 2 as well. So with an x value of 4, I'd end up with 3 times 4 minus y equals 10. And if 3 times 4 is 12, so 12 minus 2 equals 10, therefore y has to equal 2. And we end up with the same result for both equations 1 and equation 2. This proves that it doesn't matter if you sub it into equation 1 or equation 2. So if we're going to write our solution nice and neatly, we would say that x is equal to 4 and y is equal to 2. Just let me put a note here to make sure you're sure that normally we only check with one equation. The second one is just to help if you're unsure. Okay, let's check these two equations in GeoGebra and see what the solution is there. Okay, I've built this GeoGebra applet trying to keep the colour scheme in mind. So equation 1 is blue and equation 2 is pink. So if I type in x plus y equals 6, we can see the blue line there. And then for equation 2, I'm going to type in 3x minus y equals 10. And there's that line there. So no surprises that the solution is x equals 4 and y equals 2. In this applet, I've added the x equals its solution and y equals its part of the solution as well for the simultaneous equations. But you could see here we have an intersection of lines. Okay, so the blue line represents the first equation, the pink line represents the second, and their intersection is the solution. So using the elimination method has provided us the solution as we hoped. Okay, let's go back to OneNote. Now that you've seen how to use the elimination method when we have a matching pair, why don't you pause the video now and work on questions 1 and 2 in the new book or question 4 in the old book. Okay, now that you've done that, let's move on to example 30. In this example, we're not going to get two relations that have a variable with the same coefficient like we did in the last one. We'll have to use fact 1 to alter their coefficients. Okay, so for part A, we're going to need to solve these simultaneous equations. First one is y minus 3x equals 1, which I'll name equation 1, and 2y plus 5x equals 13, which I'll name equation 2. Now we can see in equation 2 that y has a coefficient of 2, and in equation 1 it has a coefficient of 1. So all I need to do is multiply the first equation by 2, and then they'll have the same coefficient of y for both equations. So 2 times equation 1 will end up being 2 times all of the left-hand side, which is y minus 3x, equal to 2 times all of the right side, which is 2 times 1, which is the same as saying 2y minus 6x equals 2. And I'm going to name this equation 3. So if I copy these two equations to the right, we can see they both have positive 2 as a coefficient for y. Therefore, equation 2 minus equation 3 will eliminate my y variable, so we can ignore the y. So let me write down equation 2 minus equation 3, and as I said, we'll eliminate the variable y. But 5x minus 6 is 11x, and that will equal 13 minus 2, which is 11, which is equivalent to saying x is equal to 1. So if I now take equation 1 and sub in x equals to 1, I'll have y minus 3 times 1 is equal to 1. So 4 minus 3 equals 1, so this is equivalent to saying y is equal to 4. So therefore our solution is x equals 1 and y equals 4. In part B, we're asked to solve the simultaneous equations 3x plus 2y equals 6 and 5x plus 3y equals 11. And I'll name them equations 1 and 2. In this example, we don't have a coefficient that multiplies easy to be equal to the coefficients of the same variable in the other equation. So we're going to have to multiply both. I'm going to focus on the coefficients of y because their lowest common multiple is 6 and they're the smallest multiplications to make. So with that in mind, 2 times 3 is 6, so I need to multiply the whole of the first equation by 3. So that is 3 times 3x plus 2y equals to 3 times 6, which becomes 9x plus 6y equals 18. And we'll call this equation 3. And again, focusing on the y coefficient, if I multiply this by 2, it's going to equal 6. So if I multiply all of equation 2 by 2, we'll end up with 10x plus 6y equals 22. And I'm going to call this equation 4. Let me copy equations 4 and 3 over here. Now we can see they both have positive 6y. So equation 4 minus equation 3 will eliminate the y. And we'll have 10x minus 9x, which is just x, plus 0y, so we can ignore that, equals 22 minus 18, which is 4. Because x equals 4, if I sub that back into equation 1, we'll have 3 times 4 plus 2y equals 6, which is 12 plus 2y equals 6. So 2y equals minus 6, and y must be equal to minus 3. Therefore our solution is x equals 4 and y equals minus 3. Alright, so let's head over to GeoGebra where I'll step through each part of this method. Not only will we see the solution is an intersection of lines, like we did in the first one, but you'll also see why fact 1 is totally justifiable too. So when we began part B in the last example, our first equation was 3x plus 2y equals 6. Now if I zoom in, notice that the y-intercept is 3 and the x-intercept is 2. And then if you recall, I multiplied the whole equation by 3, which would make this 9x plus 6y equals 18. So notice I have equation 1 as 9x plus 6y equals 18, but we still see the old equation. If I press enter, what do you expect to happen? Wow. So it's still the same graph, isn't it? We still have a y-intercept of 3, x-intercept of 2, and it doesn't matter that we multiplied both sides of the equation by 3. So you should be really happy with fact 1 by now. Alright, let's have a look at equation 2, which is 5x plus 3y equals 11. And here we go. Here we see the intercept here as 4 and minus 3. So that means x is equal to 4 and y is equal to minus 3. So the elimination method, the substitution method, all of them can still be seen as lines intersecting on a graph. I don't think I need to, but if I change this to 10x plus 6y equals 22, you'd be sure that this pink line doesn't change, right? Anyhow, you'll find the applet back in the OneNote, and that would be a good chance for you to visualize some of the simultaneous equations that we do. Of course, you can also use OneNote in the way that you saw me use in the last class. All right, let's go back to OneNote and wrap up this lesson. Okay, before I get onto the summary, actually, I do suggest that you pause the video now, and for students who have the new book, work on questions 3 and 4, and students who've got the old book, work on questions 5 and 6. All right, I'll see you in the summary. Okay, let's summarize this lesson. So this elimination method that we've used today is far more flexible than substitution. However, many people find substitution easier to use. So by all means, stick to substitution when appropriate, but this elimination method is what I use predominantly. And this is because it's more common to have linear relations that work better with this method from real-world problems. And also, as you progress in your mathematics education, you'll see that we're able to extend this method to linear relations of more than 2 variables and even non-linear relations. So for you to consider this lesson to be a success, you'll be able to understand that multiplying both sides of an equation produces an equivalent equation, i.e. fact 1. Know how to use the lowest common multiple to obtain a matching pair of terms in 2 equations, and be able to eliminate a pronumeral by adding or subtracting 2 equations with a matching pair, which is fact 2. Of course, we'll check this off in class, which is where I'll see you next, unless you see another video between now and then. See ya.